Hi everyone, so we are continuing the course Advanced Algorithms. So we're still in the part 3, the problem solving paradigm, and we're following the textbook of Dr. Halim. So we have reached the divide and conquer part 2 in this chapter. So we'll be covering what divide and conquer, and we'll see some interesting usages of binary trees and trees in general. So as the overview, so this slide you've seen it the last time with Dr. Siba, so where we check the different types of paradigms. However, today we'll focus on divide and conquer schemes. So you'll be surprised that you've been doing and practicing divide and conquer and programming using the scheme from the first year. So what's divide and conquer? So it's based on recursion. So we have recursive calls, and what we will do is that recursively we'll break down the problem into a smaller problem that is easier to solve, and then we will sum these sub-problems in order to solve the original one. So it's the natural recursive stuff that we do. So first we divide the big problem into smaller sub-problems, then recursively we will try to solve these smaller problems, and then we will combine the answers in order to give an answer for the original problem. So can we use divide and conquer in every problem? Of course not, because some problems cannot be subdivided into smaller problems that are easier to solve. So as for to see how it works, so let's assume that we have the size of the original problem is equal to n, so we try to subdivide this problem into b smaller problems. So we have n over b sub problems, and then we'll try recursively to solve these smaller problems, and then we will combine all the solution of these sub problems. So in coding, so we have a function which is recursive. So the stopping condition is where the problem p is very small, and we know how to compute it very easily. So we return the answer, the solution of the problem p, and then we'll try, if it's not the case, so we'll not to subdivide, we'll try to subdivide this problem into smaller problems. Here we are subdividing the problem into b sub problems, and then recursively we will call the same function, which is divide and conquer. As parameter, we will place the smaller sub problems, and then we will combine the solution of each such sub problems. So where we have used divide and conquer, so basically all the binary search, merge sort, and quick sorts, the problems that we have covered, especially in data structure in last year and the second year, we have used divide and conquer, since all of these uses the divide and conquer and recursion in trying to solve all these problems. So as an example, for example, when looking in a book, so we are using a binary search here. You are finding a name, you are finding like an index, you want to search for a keyword, so you will probably use a binary search because it's quicker than using a linear search. An example also like finding your car in the parking lot. So if the parking lots are numbered, so you jump from number to number, you don't need to follow the numbers in sequential order. So what are the advantages and disadvantages of divide and conquer? So for the advantages, so the divide and conquer can solve some of the most difficult problems like the towers of Hanoi, and it affords us some parallelism, since we can solve each sub-problem on its own. And if we can parallelism, if we have a machine that we can do such stuff, we can take advantage of the parallelism of divide and conquer scheme. As for the disadvantages, so it's first, the recursion is slow, so we have the overhead, we have the stack and all those stuff, and the memory reservation and the heap. So sometimes it's more complicated than an iterative search. For example, here we have an example which is that if we have an array of n elements and we need to sum all these elements, so obviously we'll not do a divide and conquer solution. It's better, it's easier to do just a linear sum. So we skim over the array and we sum the elements. So if we want to do it using a divide and conquer scheme, so we need to divide the array into two sub arrays and recursively and stuff till we reach an array of size 1, and we will return the element, and then we will sum all of the sub arrays. So it's too cumbersome here to do it using divide and conquer paradigm. So as for the application, we can use it in binary search, merge sort, quick sort, the median finding, min and max, matrix multiplication, and the closest pair. We will see some of these applications later on. So as the binary search, so we have covered it in the last year. So we check the middle one if I need to move to the right or I move to the left, depends on the condition, and the complexity will fall into log m. So we have a built-in libraries either in C++ or in Java. So in C++ we have the function lower bound and upper bound. So we'll see it next in the next slide. And in Java in the collections we have the function which is called binary search. So in the left part here we have the C++ code, and here we have the Java. So it's basically the same. So we have an array. So there is multiple elements. So we have created a vector and sort these elements. So as you can see, after sorting we will have 3 10s, and then we will have 3 20s and 2 30s. So and then we are looking for 20. So 20, it's repeated 3 times. So in lower bound, it gives us the index of the first 20, and however the upper bound, it will give us the index of the first element greater than 20. So at the end we will have the output. So lower bound would be equal to position 3, so 0 1 2 3, and the upper bound, so the first index greater than 20 is here, which is equal to 6. So in Java we have the function which is called binary search in the collection. So we have an array. So we have sorted the array using the function sort. We have looked for the element 10. So 10 it's equal to index 0 1 2 3 when the array is sorted. So the output will be equal to 3. However, if I want to search 13, the answer would be equal to -5. Why? Because in the sorted array, and if 30 would be there, it should be here. So it should be at index 4. So since 4 doesn't exist, the index 4 is not equal to 13. So it will return -4, and -1, since the function returns -1, so it will be equal to a -5. So an index which is negative would mean that the element is not in the array. So as another example is the bisection method. So in the bisection method, we try to search the root of a function. It means that if I have f of x, I need to find x for which f of x is equal to 0. So in the animation here, we need to find this solution. So what we can do is that we pick two numbers, a and b. So here in the animation 3 and 4. And then what I will do, I will find the median, so the a plus b over 2, and I will check the value of f of the average of these two numbers. So I will see that it's not equal to 0, it's here negative. So I need to reduce or increment one of these a or b, so the borders. So I will try this. So it means that I need to move to this part. So I will take 3 and 3.5 and then take the middle one, and as far as we go. So we'll try to iterate till we reach the f of x equal to 0. So there's some conditions. First, that a and b, the functions of a and b, the image should be of different signs. So one is positive and the other one is negative. So let's see an example. So we have an example that you want to buy a car. So you went to a bank for a loan, and you need to pay some money for a month. So you have a quantity of money and you have to pay it for m months. So this is the natural case. So you want to buy a house, you want to pay it for 15 years, 30 years. So you need to know how much you need to pay on each month. So usually you have here a car. So so the original price is $v, and there's an interest that the bank charges, which is I, and you want to know how many months you need to pay in order to fulfill all these payments. So for another example, the same example was with numerical values. We have D. So your monthly payment is like that in dollar. You have to pay in 2 months. The original price is 1,000 and the interest is 10%. So after the first month, so since the original price is 1,000, sorry, and the interest is 10, so we will multiply this number by 1.1. So 1 because for the original price, and 0.1 is the 10%, the additional 10% on the original price. So this is the amount that you should pay, it's the amount, the total amount after 1 month. And if you pay a monthly payment is 576.19, so you will end up, after you pay this amount after the first month, you will end with this amount of money. So you need to pay this in the second month. In the second month also you need to pay the 10% interest, and if you pay this amount, so this one would be equal to this one, you will end up with 0. So if you take a loan of 1,000 and you pay it over 2 months, just 2 months, you need to pay in each month $576.19. So this is the solution. However, the question is usually it's the reverse process. I need to pay this amount of money. I know how many months I need to pay that. I know the interest, and I need to calculate the amount of money. So this is the solution of this function. So I have multiple parameters, the m, the v, and the I, and I need to find d such that this function is equal to 0. So we will use the bisection method. So to solve it, as I have said, we need to pick two numbers as starting point, and of course the f of a and f of b should be of opposite sign. So one is positive and one of negative. So how we can pick a and b? So a should be the smallest possible. For example, if I want to pay, at least I can pay one cent, so it's the minimum. And b, it could be the amount that I can pay just after 1 month. So here it would be equal to 1,100. So those are the extreme values. So of course I will not pay 1 cent. Of course I will not pay all the loan after 1 month. So I can wait 1 month and then pay all the amount. So how the bisection method works? So we'll start with a was equal 001 and b equal 1,100. Then I will take the average, which is equal to 550.005, and then I will calculate the function. So let's run it for this example. So first I have 1,000. I will multiply it by 1.1, and then I will subtract the amount of payment. So now I'm considering that I will pay this amount. So I need it will remain to pay this on the second month. So on the second month I will pay I'll multiply it by 1.1, and I'll subtract the value. I didn't reach 0. It means there's more money I need to pay for the third month. So what does it mean? It means that the number here is too small. I need to pay more in order to reach here 0. So as I have seen, it's undershoot. What does it mean, undershoot? It means that I should pay more. This is underestimating. The amount here is too small. So what I should do, I should increase the d. So d here should be increased. So what should I do? So of course, if I will take the range here between a and b, I should increase a. So what I will do in the next iteration, a would be equal to the average, which is equal to 550, and I will keep b, and I will do the average again. So it will be equal to 825, and then I will repeat the same calculus, and this time we will see that it will be too much. So it's overshoot. So it will be too much. So what I should do now, I should decrease the element. So what does it mean to decrease d? It means d here, the biggest element. It means it's too much. So what I will do now is I will keep a, and b would be equal to d, and like that we will continue in the same manner till, for example, the difference here between the different calculations would be equal to epsilon. So the errors here between each these iteration would be less than an epsilon, and the answer would be equal to 576. So why it's very important, why it's very beneficial? Because the bisection method, it needs just log of b minus l over epsilon iteration. So it's very minimal. In the example we have seen, so this is the b minus a, and if we take epsilon equal to 1 to the power minus 9, so we just need 40 iteration. And if we want to go smaller, so if we want an epsilon smaller, even smaller, we can we just need 60 iteration. So this is very small on the number of possibilities if you want to try it by your hand. So, and the bisection method we can write you can write it as if you are writing binary search function. So let's see it. So we have a for loop. So we need to calculate first the number of iterations. So just we make the log 2 of b minus a over epsilon. So here, for example, it's approximately equal to 40. So we will loop till 50. So it's 50 times. It's not too much. So, and at each iteration, what we'll do, we'll calculate the middle. So it's low plus high over 2, and then we will check if the function of the middle is greater than 0. It means that I need to pay more, so low would be equal to middle, otherwise high will be equal to middle. So after these 50 iterations, the middle will contain the exact value of D. So this is for the bisection method. We'll do two applications on the divide and conquer, which is the segment tree, the range minimum query, and Fenwick tree for range sum query. So those two parts are not in chapter 3 but in chapter 2. So segment 3, let's start. So the segment 3, or it's called the range minimum query, is very efficient data structure for answering dynamic range query. So dynamic, we will see it just in a while. Range query, it means, for example, here an example, you want to find the minimum element in an array or within a range in this array. So you can either do it linearly, so it will take complexity of n. However, we can do it in less than n. So this is mostly known as a range minimum query or RMQ problem. So let's take an example. We have this array, we have the indices, and we have the values, and then we were asked, for example, what is the minimum element between the index 1 and index 3. So forcibly we will say it's index 2 because 13 is smaller than 17 or 9, so it's index 2. So you can have those questions. What is the minimum elements between the index 0 or 1? So it will be equal to the index 1 and so on. So there are multiple ways to implement the RMQ. So the one trivial, as you have said, is the linear one, which is equal to O of n. However, when n is large and there are many queries, so it would be impossible, or it's very costly in terms of complexity to solve it in a linear fashion. So what we will do is that we will use a segment tree. So it's like a heap that we have seen in the next year data structure. So a heap can be represented by an array, and we know how we move into the children, so we'll recall it here. So we have an array here called st for segment 3. So the index 0 will be skipped, so we'll start from index 1. So the children, so if we have a tree like this, and this one is of index 1, so the array is here 0 1 2 3. We have here a b c, so we have a here, so b would be an index 0, will not use it, so a will be in an index 1, so its children will be in equal b and c. So this one is equal, if one is at index I, this one would be equal to I, and this one it's 2I plus 1. So maybe you have remembered that, or you need to review last year course. So we will use the value in st of b in the segment 3 for the range queries function. So let's see how we will do that. So we have an array, and we will try to have a segment tree. So the root would be equal the segment tree of all the array. So it's between 0 and n-1. The example here is the same as above. So it's between 0 and 6, since we have 7 elements. So when we go to the left, so we will split each segment into 2. So first one, we'll call it left and right. We'll do left and left plus r over 2. So left would be the same 0 and 6. I will do 6 plus 0 equals 6. 6 over 2 equals 3. So this one would be equal to 0, 3, and of course the second one would be equal to 4 and 6, and so on. We will continue to subdivide each segment till we reach the segment which is equal. So left and r would be equal to each other, and of course here the minimum would be equal to L or R. So it's very obvious. However, in the st, in the array, so the elements will be written level by level. So this is the first element, this is the second element, the third, fourth, and 5, as we have seen in a heap tree. So this is for constructing the st. So let's see the code. So we have here two functions, left and right. So we'll take an index p, and then so we know that the left children is at 2 multiple p, and the right one is at 2 multiple plus 1. So here we have the right shift of 1. So for example, if I have p equal to 2, so 2 in base 10, in base 2 it will be equal to 10 0, and I want to do the right shift. So if I do the right shift of 1, so it will be equal 10, and I will add a 0 here. So this it will be equal, sorry, it will be equal to 4. And again, shift of 1 plus 1 will be equal to plus 1 base 2, so it will be equal to 0, 1, 0. So it will be equal to 5 in base 10. So this is very quick since we are using the binary operators. So let's move. So how to build this tree? So when we are building, we have the left and right. So the index of the left and the index of right. So we're using divide and conquer. So when we reach left equal to right, it means at the end of the tree. So we have left and right equal to each other. So obviously the minimum is one of these L or R. So it's the same elements. However, recursively, I'll try to build the left tree and to build the right tree. So I just need to modify the P. So here it will be equal either left, either right. The left index would be equal to L and the right would be equal left plus R over 2. At the opposite way, in the right side, the left part will be equal left plus R over 2 plus 1 and the right will be stay the same. So as for each one of the left and right, so in order to calculate the minimum, let's see here. So we will place in P1 the ST of left of P. So we will place the minimum that we are calculating while we are going up, and then we'll see which one gives me the least minimum. So if the left part would give me the value is less than the right part, so I will keep the index of the left, or I will keep the index of the right. So as an example here, we have, so here we do not have the values. So we have here the minimum is index 4, between 4 and 5. However, when we go up, the minimum between the index 4 and index 5 is index number 5. So why? Because while we get the index here 4 and 5, we check which one is the minimum. So it's here the function, it's here the test, and we will save either P1 or P2. So this is the implementation for the creation of the segment tree. We didn't yet see how we can use it to answer the queries. So as we have seen, so if you want to answer those questions, those queries, so we will not use a complexity of n, but a complexity around of log of n. So whenever I want to range minimum query of II, if I want to find the minimum index between a range where are the same index, so it's trivial, so it's I itself. However, if I want to find the minimum query, range minimum query between two indices which are different, so what I can do is that I will try to find it again by a divide and conquer scheme. Start by I, and the j would be equal to I plus j plus 1, and then find the other way, and then check the same element. So as we have made here, in fact, but we will do it as a range query. So let's see an example before writing the code. So we have the tree here, and we have the indices, and I want to find the range minimum query between 1 and 3. So when I'm looking here at the tree, at first we have 0, 6. So obviously 1, 3. So I will. It's not 0, 6. So it's not equal. So I should look left and right. I need to check in the code. I need to check. So whenever I look at the right, I see 4, 6. So 4, 6. So 1, 3 is not in 4, 6. So obviously I will return minus 1. So I should look in the left part. So this is done recursively. I should look left and right. So right, it will end directly. In 0, 3, I look. So 0, 3. So 0, it's too far from 1, and however 3 is inside. So the answer is not here. So again, I cannot settle with this one. I will check left and right. I will see here in the left 0, 1, 0, 1. I don't need the 0, however I need the 1. It means the value here 1, it will not help me. So I need also to go left and right. 0, 0, it's not between 1 and 3. So I will return minus 1 as it looked here. 1, okay, I need it because it's in the range minimum query. So I return the index of the minimum, which is equal 1 to here. So between 1 and minus 1, of course, it will equal to 1. So here I will move to the right part. So right part, I have 2, 3. 2, 3, it's inside the 3, 1, 3. So I don't need to check those black boxes. I just settle with the answer, which is here equal to 2. So now I have 2, and now I have 1. So what should I do? I need to choose either 1 or 2. How can I choose that? I will need to check the original array. So I need to check the index 1 and index 2. So we will see that index 2 is the smaller element. So I will keep 2. And then between 2 and minus 1, I will move 2, and I will have the answer 2 for the range minimum query between 1 and 3. So it's all explained here in detail. So let's see an example more. So let's build the tree, the following tree. It contains the element, the 7 elements. So it's between 0 and 6. So here the equal to 5, it's already at the end. So whenever we construct the tree at the end, we will have the index 5. So we will have 0 and 5, and then we will have two children left and right, 0, 3, and 4, 5. And then for each element, we will subdivide the tree. So, and then we need the range query of 4, 6. So 4, 6, we check first on the right side. So there's no 4, 6 here. We check the left and we check the right, and we see that at the right part we have the same range minimum query, which is 4, 6, which is equal to 5. So 5 and minus 1 here, because it's out of bound, we will return 5 to the function. So it's written, we have 5 in red, 5 in red, and minus 1 in red. So let's write the function of range minimum query. So as you have seen, at each time we need to check the left and right. So I will start with the recursive calls. So we'll try the RMQ at the left tree and right tree. So here are the original indices. So the range minimum query, those ones. So we need to keep them as long as we go in the tree. And we have here the left and right, the left and right indices of the left and right subtree. So it depends on P. So we need to check the range minimum query on the left and on the right, and we will check if P1 is equal to minus 1 is on the left part. I have minus 1. It means the answer, it would be in P2, and reversely, if P2 is equal to minus 1, I will return P1. And in the case I have two answers, I need to check the array in order to pick the smallest index. So this is the recursive call and the combination. However, when I need to AND, there's two possibilities. So either we are outside the query range. For example, I'm looking for 3, 4, 6, and I reach a place where 0, 3. So it's out of range. So I will return directly minus 1. However, if I'm inside the range, for example, here, I'm directly inside the range, I directly return the ST of P. So here again you see the C++ code and the Java code. They are obviously the same, nothing changes, just there's the private here. So I will repeat. So we'll do the recursive calculation. So on the left, on the right, so if one of these left or right values, the P's, the indices, is equal to minus 1, I will return the other value. If I have two values other than minus 1, I will check it with the array and pick the smallest indices index. So if for the stopping condition, so either we have a segment that is outside the query range, or we have an inside the query range. So this is the implementation for the query range query. So when we use that, you should pay attention that if the segment 3 is static, so it overkills. It means it takes too much time. So it's better if you have a static array that doesn't change, it's better to do a dynamic solution, because it will take less time. However, if it's dynamic, if we add or modify the array, as long as we are dealing with an exercise, so it's better to use a segment tree. So let's see an example. We have the original tree here, and then we have changed the element 11 into 99. So what I should do, I will not modify all the tree. So I just need to modify the branch which contains a 5. So this is one, it's here. I just need that. So I'll start from the end, from the leaf, and I'll go up and I'll modify all the stuff. So it's easy. I'll just need to modify one branch to modify all the tree. So this is the advantage of using this kind of segment tree when we have a lot of modification, when we have a lot of changes of the elements in the array. So for the update, you just need, as I have said, one pass, one route from root to the pass. So it takes us just log n. So the DP solution. So later when we cover the DP, this modification, it would need us n log n, which is too much for an update. So for that we should use the segment tree. So for the visualization, you can check the link here to check how we can add, remove, and all stuff of this concerning segments tree. So this was for the segment tree. We'll move to binary index Fenwick tree. So in Fenwick tree, we will use it for implementing the cumulative frequency in tables. So as an example, we have M students, 11 students, so each one there's a test and he can get a grade. A grade is between 1 and 10. So in the next slides we will see the frequency. So the frequency would be equal between, for each test score between 1 and 10, so or 0 maybe, since for example here no one got 1 over 10. And the cumulative frequency, you should pay attention, it's cumulative. It means the frequency of the element from 1 till the element I. So let's see the example. We have here the scores, so the different scores 0, 1, 2, 3 to 10. Here we have the frequency, so the number 1 doesn't appear. 2, there's just one student who got 1. The cumulative frequency is the sum up to this index. So for example, the frequency of 5 is the sum up to this index. The frequency of 7 is again the sum up to this index. So how can we do that? So what we'll do is that the operation, I have for example the frequency is here, the cumulative frequency is equal to 10, and I know that, how can I calculate that? It's equal to 1 plus the cumulative frequency of the element just behind of me. Same here, it's 0 plus 11, so it's equal to the cumulative frequency to the element just behind me plus my frequency. So it's cumulative. So, and then we can ask questions about the different frequency, the range frequencies, and the range sum queries. So we'll end up with sometimes the same questions as we have seen in the segment 3. So as we have seen, so the frequency tables, the Fenwick binary tree, then we'll see it. It can answer us to the range sum queries. So range sum queries, if it's the sum of the frequencies between a range. So as an example, range sum query for 1, 1, between 1 and 1, it will be equal to 0. The range sum query between 1 and 8, so it will be equal to 10. So we just look at 10. So range sum query is the sum of frequencies between 1 and 8. So whenever I need to find a range sum query, for example, between 4 and 6, so it's easy. So I find the range sum query between 1 and 6, and then I will subtract it from range of sum query of 3. So range of sum query between ij, it's equal to range sum query between I1 and j minus 1 and I minus 1. So I need to subtract just from the next element 1. So the range sum query of 4, 6 is equal to range sum query of 1, 6 minus the range sum query of 1, 3, which is equal to 7, minus 1 would be equal to 6. So there are 6 grades between 4 and 6. So this is the meaning of range sum query. So how can we do that? So we'll use a Fenwick tree, which are very efficient, and we will be using some bit manipulation. So the function that we'll be using is the least significant one of numbers. So we have covered it in the previous part. So it's equal to I and minus I. So let's take an example. For example, if I have 5 in base 10, so it's equal to 1, 0, 1 in base 2. So the least significant one is this one. So how can I do that? So this 1, 0, 1 is I. So minus I is the 2's complement. It's example here. So let's do this one. So we have t, which is equal to I and minus I. So for example, we have I equal to 40. So this is 40 in base 2, and minus I is the 2's complement. So in the 2's complement, I will start from right to left, and I will keep the same element unless I find the first one. The first one I'll keep it, and after the first one I flip all the bits. So 0 will become 1 and 1 will become 0, and then I will do I and minus I. So I will find that the least significant bit is this one, which is equal to 8. So this operation will be using it in the Fenwick tree. So how we will do that? So in Fenwick tree we'll also use it use an array. So it's a simple array. The trick here is that the indexes, so how we will use the indexes is by the trees will be indexed by the bits of its integer key. So you just need to wait a little bit to let me explain it in the next slide. So and the integers of course will be fall within the range 1, and again we will skip index 0. So we will have here scores between 1 and 10. We have 11 data points, and the size would be equal to 10. So the Fenwick tree array would be equal, so the name of the array would be equal to ft. So the indexes, so this is here the trick, the index by the bits of its integer key. So here we have ft of I. So ft of I will store element of I, ls1, I, ls1 plus 1. So all this stuff. So what does it mean? Here we have the visual. So it means that the index 4 in ft of 4, it will store the values of ft of 3, ft of 1, and ft of 1. So let me do the calculations. So let me just review here the elements. So here we have the value of ft, here we have the range, so it's what it covers. So for example, let's take the ft of 4. So ft of 4, it will is responsible for the range from 1 to 4. Look at the range. So how can we calculate that? So it's written here that it will cover this range from I minus ls1 of I plus 1 till I. It's written here more elegantly. So I minus ls1 of I plus 1 till I. So here I have 4. So I equal to 4. I have the range 4 till 4. 4 minus ls1 of I plus 1. What is the ls1 of I of 4? So 4 in base 10, it's equal to 100 in base 2. So ls1 of I, the first significant bit, is also here. So ls1 of I, ls1 of 4 is also equal to 4. So 4 minus 4 plus 1 plus 4. So the range would be equal to 1, 4. So 4 is responsible of the range 1, 4. Let's do 6. 6. Let me erase. So in 6, we have 6 plus minus 1 and 6. So 6 in base 2 is equal to 110. 110, this is 6. ls1 of 6, what's the least significant bit is 1, is this. So this one is equal to 2. So I, here minus and plus, minus 2 plus 1, 6 minus 2 equal 4, 4 plus 1 equal 5, so 5, 6. So ft of 6, it's responsible just for 5 and 6, and this is, and so on. 7 is responsible just for 7. 8 is responsible for the range 1 of 8. So if I found in value of ft of 8, I have the range sum query of all the elements from 1 to 8. So obviously when doing the code, the implementation, you will not see that. So you need to find it directly using the code. So, and you see it's very easy. So this is for the constructing of the tree, the construction. However, how to obtain the cumulative frequency of 1b, so which is RSQ-b. So what we will do is that we will do the summation. So for example, if I want to find the RSQ of 5, so 5 I know of 6, sorry, I know that in 6 there's the summation between 5 and 6, the range sum query of 5, 6. However, I need to also have the other one. So I need to sum the ft of 6 plus ft of 4. But how should I know that? How should I calculate ft of 4? So here is the answer. So what I will do is that I do multiple summations. So we simply add ft of v prime. So how can we calculate those stuff, b prime, b second? So at each time I will subtract the least significant one. So in 6, so 6 equal to 110 in base 2. What's the least significant one? Is equal to 0, 1, which is equal to 2. So 6 minus 2 would be equal to 4. So whenever I'm calculating ft of 6, I need to sum ft of 6 plus ft of 4 plus till we reach 0. Let's see 4. 4 is equal to 100. What's the least significant bit? Is also 100. 4 minus 4 equal to 0. So here we will add ft of 0. However, as we know, there is nothing in ft of 0 because it's skipped. So it's all explained here. So this is how we calculate the range sum query for an index of the tree. So what if we have not just one. I don't want from the answer from 1 to b, I want it from a to b. So again, as we have seen, we do the range sum query of b minus the range sum query of a minus 1. So let's see. So again, it's very important here the updating. If I want to modify some of the elements, so I don't look backward, I look forward. So for example, if I want to modify 5, I just look horizontally, so the one that I can I can change. So here I just need to modify this element, and I need to modify this element. So how can I find those elements? Again, I just need to add to my index 5 the least significant bit to order to find all these elements. Of course, I will continue till I reach the elements n. So this is for the updating. Let's see the code. So we have here the function least1, which is just to return the element and the negation of it. So the two's complement. So for the Fenwick tree, so we have the ft. So at first we put zeros in all the array, especially for ft of 0, since we need to end there. And for the range sum query, so I will start from b. At each time I will subtract the least significant bit, and I will add the ft of this element. So it's very easy. For the range sum query between a and b, so it's the range sum query of b minus the range sum query of a minus 1. For the adjustment, again, it's the same as the range sum query. However, I will move forward. I will always add the least sum bit until we reach the size of the Fenwick tree. At each time, I will modify just those elements by adding the new element, the v element. So as the visualization, again, you can check the link above to see how can you work with the Fenwick tree. So this is for this part of the course, and you will have 4 exercises to do till next week. And thanks for watching, and stay safe.